Yes. Good evening, all of you. Right now, starting methods of DC motor. So actually, it is not there for GATE syllabus now. So first of all, why we need a starting method means not only giving supply with a reduced starting current, because at the time of starting, what is the speed of motor? Supply given, then speed is zero. When speed zero, EMF induced in armature is zero, that is back EMF zero. Because of that, the armature current is V minus 0 by RA. This is very high armature current because supply voltage 220 let armature resistance less than 1 ohm, which is very high current. Due to this high current, there is a chance of armature winding burning or melting. So we need to limit that high current. Now what we are doing in all these starting methods, what we will do to reduce that armature current at the time of starting is, tell me, IA starting equals to voltage divided by armature resistance, back EMF 0. In order to limit that starting current, what we are implementing in starters? To reduce the starting current, what we are implementing, you can reduce the voltage or you can increase resistance by adding some external resistance. So what we are doing in the starters? What we are doing in starters? So we are doing that, adding a resistor in series with armature externally. Adding a resistor in series with armature externally. Okay. So like that, we will reduce the current drawn by armature at the time of starting. Now to reduce that, we are using starters. There are three starters totally. One is 2-point starter, 2-point starter. Second, 3-point starter. And third one, 4-point starter. 4-point starter. Yes, during running progress, when the starts motor pick up the speed, during that we will remove the resistor, so no problem. See, there are three starters. 2-point we use for series motors. 2-point is suitable for series motors, and remaining shunt and compound and all motors we use 3-point starter. Okay. Now out of this, now we are discussing only 3-point starter, because if you know about 3-point, you will understand 2-point, and you will also understand 4-point, 3-point. 99% both are same. Both are 99% same. I will show you what is difference in 4-point starter just. Okay. So 2-point you can understand if you read also by understanding the 3-point starter. Now we are going to see only 3-point starter, how it will function, how it is limiting starting current, how it will protect the motor from overload condition also. In all these starting methods, we also have overload protection. Overload, because every motor should have overload protection. Otherwise, whenever any high current comes to the motor will burn. So we need a protection. So starter means limiting starting current and also protecting the motor. Both will be there in this. Okay. Right. 3-point starter. Starting. 3-point starter. Draw the figure simultaneously. Not only for ESC, for after this we see losses and efficiency, that is there for GATE examination also. Okay. Losses, efficiency calculations are there for GATE. And after that we see testing. The testing is only for ESC. GATE it is not having testing. Draw the figure. Yes, same as it is. Yes, for state level examination, each and every topic is there. Everything is there for competitive examinations. Today is lost. Yes, we have to draw diagram also, because in ESC mains examination, you may get a question like explain about 3-point starter operation. Okay, so that is important. So you should get each and every diagram you have to draw. But for gate and objective type of examinations, you no need to learn diagrams and uh, derivations and all. But for engineering services mains examination, you must have complete information with you. Conventional examinations. So transformer and induction motor, new batches. We don't know when it is. Completed all of it. See, there is no difficulty in drawing drag diagrams. If you know how it operates, the function of the starter, you will draw it anytime. So don't by heart the figures. Learn the operation, how it operate enough. Yes, 2 to 3 times practice. Yes, GATE students also, most of the people can get through ESC prelims, because in the prelims examination, whatever you prepared for GATE, more than enough. Almost 95% it is enough. Okay, and GATE, compared to GATE questions, ESC questions easier. And only the thing required is some general studies. Okay, that about that you need to take care enough. Okay, see the operation of the starter. So this is a spring here. This is a spring. At the center of the handle we have spring, spherical spring it is. Yes, yes, that general studies is enough for PSUs also, state PSUs. Okay, listen here. This is our off position. This is off position. This is on position. Now handle is at off position initially. See, in a starter we have number of resistors. Let R1, R1, R2, R3, R4, R5. 5 resistors are there in this. 5 resistors means whatever these points are there, these points we call in starter studs. These points we call studs in the starter. 1, 2, 3, 4, 5, 6. 6 studs are there total in this. So in the labs, if you observe in the starter inside, this points is nothing but bolts. A big size bolts will be there. Big size bolts. Okay, that is only studs here. That is only stud. Okay, there are number of resistors. Remember, if there are 5 resistors, if there are n equal to 5 resistors in a starter, how many studs will be there in the starter? N plus 1 studs will be there always. If there are n resistors, n plus 1 studs will be there in a starter. Because sometimes in examinations they used to ask, calculate the number of resistors required, number of resistors to limit starting current, or calculate number of studs required. If you know number of resistors are 5, number of studs will be 5 plus 1, 6. Okay, But anyhow, I'm not going to give right now for calculation of resistors and all, because only in ESC mains examination they will ask you what is the values of this resistor also. R1 how much, R2 how much. See, in this starter, any starter, whatever the resistors are there here, R1, R2, R3, R4, R5, these are not same resistors. These are grading. We will grade these resistors such that the first resistance is the higher value, second is little less than, third still reduce, fourth still reduce, fifth still reduces. Like that, step by step, that resistor values reduce. Like that, we will design that resistors to limit the armature current. Okay, these resistors are never having same values. Okay, they are different. In only in mains examination, we have the previous questions also on this calculation of these resistors also. But right now we are not going to do all these, because these questions you never get in the prelims examination or gate examination or any competitive examination, because each question will take minimum 15 to 20 minutes to solve. Calculation of these resistors will take minimum 15 to 20 minutes. So no objective type of question will ask calculate these resistors. Okay, let's see only the operation, how it will protect from overload, and what is the drawback of 3-point starter. Okay, see first. In this starter, we have two magnets. One is called holding magnet. This is okay. This is holding magnet or holding coil we call. And another one is OR. OR means overload release magnet. So whenever overload occurs, automatically this magnet will operate and disconnect the supply to motor. Observe now. Handle initially off position. So I think each and every one has started in your lab this starter, right? Observe now. It is off position. First, close the DPST. Dipole single throw. Close DPST means supply given. Even supply given, motor will not start because it is off position still. Now, when you touch the handle, let us move the handle off to first stud. When you touch the handle to first stud, now current flows. Observe here from this first stud, current is coming through this. This is the load current. The current will come in this and comes here. Through this internally handle, there is a wire. Through that, current will come and it will touch the first stud. Now from here, this is the field current direction, ISH. Check ISH. Field winding or field current is flowing through holding coil and then comes to the field winding. And armature current will come in all the resistors, in all these resistors, and then enters into armature. This is armature current. Now tell me, at first stud, what is the armature current? The voltage is V divided by armature resistance RA plus total resistance R1 plus R2 plus R3 plus R4 plus R5. That is, I'm taking as capital R. Total resistance in starter. This is the current once you touch the handle at stud 1. Like that, whenever you move the handle from stud 1 to stud 2. Now from this, what is the direction of current? Tell me. IA will flow only from here. Means some resistance R1 is eliminated in series with armature. Step by step, we will remove the resistors in series with armature. But at the same time, the current is flowing, field current is flowing from R1 back like this. This is the field current. In series with field winding, resistance increase. So you may get questions here. Important is, once the handle is touched with first stud, what is the field current? What is the armature current at that time? Field current is maximum. Armature current is minimum. At stud 1, field current is maximum, armature current is minimum. Why minimum? All resistors are added now. That's why current is minimum at that time. And what is field current? Directly flowing like this. This is maximum current. Now when you move the handle to stud 2 from 1 to 2, when you shift the handle will touch 2. Then field current will go like this. Means in series with field winding, resistance added R1. Then it is coming like this. And armature current will flow from R2 only. Like that, whenever handle is moving from stud 2 to stud 3, stud 2 to stud 3, again armature current little resistance is removed. Now armature current in this direction and field current in this direction. Okay, this is the field current. So like that, let us move the handle to last stud. Once you move the handle at last stud, there is one magnet we placed. Now, what is the armature current from this? The armature current is directly going to armature. No resistors in series with armature. Only during starting there is a resistor. Once it is connected to last stud or on position, we call, from there armature current directly flows. No resistor now in series with armature, because whenever we are moving stud by stud, during that the speed of motor increases here. Whenever speed increase, back EMF will start increasing. When back EMF increase, automatically current decrease. Then you can remove the resistor. No problem. Like that, step by step, we will move the handle, but not at a time like this. That's why during starting in labs also, the people will tell you, don't start quickly, start slowly that handle. Slowly we have to move the handle stud by stud, not immediately. So what happens immediately if you move? Motor has to rotate, allow the motor to rotate for some time. Because of inertia, no motor will rotate instantly when you move the from off to on position. Allow the motor, whenever motor rotates some speed, back EMF will be there. That back EMF will limit the armature current. Then no problem for us. Okay. Now finally, when handle we placed at sixth stud, last stud, there is a magnet here. So field current is flowing through the magnet, electromagnet it is. Due to that current, there is some strength of the magnet. Now handle will attract it towards this magnet. So once you leave the hand at the on position also, handle will not come back, because handle is attracted to this magnet. So handle is continuously at sixth stud only. Now motor is running at rated speed. Okay. Now we started the motor. Let us move the handle from off to on position, stud by stud slowly. And finally at sixth stud, the handle will be attracted by the magnet. Now handle is at on position only. Motor is starts rotating at rated speed. Let us increase the load on motor. Let us increase the load on motor. What load? In your lab, we do brake test. We do the brake test, right? Now let us increase the brake test or brake on this. Our load increases. Whenever load increase, what is the current drawn by motor? Load current. Load current increases or not? Yes. If load increase, current increase. Load increase, current increase. Let us assume this motor rated capacity is 20 amperes. Rated current of this motor 20. Means up to 20 we can operate safe, no problem. But let us consider the load is increased beyond 20 amperes, 22 amps now. Still no problem, because for every motor practically we provide some additional range that is not showing outside. Suppose every motor they give, suppose 10 amps is the rated current, but you can operate up to 12 amps. That like the 2-3 amps, no problem for motors. 2-3 amperes it will operate. Okay. So up to 22 we can operate, 23 also you can operate. Now I will fix the overload protection for 25 amperes. So more than 25 should not flow in the motor. Like that I will arrange. How I will arrange is, see, this is one magnet here, OR magnet we call. So this magnet is fixed one. It cannot move. But below that, see this is a magnet. Below that magnet I will place one rod here. One rod I attach with a screw. This is a screw here. This is a screw. One side it is fixed. Now this iron can move like this. This iron can move like this. One side it is fixed. Okay. Now observe. I will arrange this magnet such that whenever there is 25 ampere through this magnet. So what is the nature of electromagnet? If more current is there in the winding, more strength of the magnet. If less current, less strength. Now I will arrange this magnet such that whenever 25 amps is going through this magnet will have some strength so that it will attract the iron below that. Now iron is attracted. This iron, near to this iron, I kept two wires. Two wires I placed like this. Two wires I placed, fixed, copper wires. Whenever this iron comes towards magnet, it will touch the 2 points or two copper wires shorted. The 2 points are shorted AB. Once AB shorted, AB means this is A, this is B. This is shorted. Once AB shorted, now current will not go into this holding coil. Now current will flow like this directly. When there is no current going in the magnet, what is the strength of magnet? Reduces. That is called demagnetized. Now the magnet is demagnetized. Previously, there is a current, there is a strength of magnet greater than spring force. So whenever we move the handle from off to on position, the spring at the bottom will tighten. That there is some spring force. Now, whenever there is strength of magnet becomes zero, the spring what will do? The spring will take the handle automatically to off position. So automatically handle come back to off position, means the load current is very high. That's why the handle automatically come back to off position. So it is protected the motor from overload operation. Is it clear? All of you. Still any doubt in this? Why response is very slow today? Yes, at overload, at one time it starts. Why the name 3 point? 3 points are there here. L, F, A. The 3 points we indicate in a starter. See, L is 1 point. In a starter, L is 1 point, F is 1 point, A is 1 point. That is called 3 point. 2 point is LA, because in series motor, line, armature and field both in same line. That's why A only we indicate. F we don't consider. But in shunt motor, field is separate, armature is separate. That's why it is LF. 4 point means two line terminals will come, one field, one armature. That is 4 point. Very good. Yes, above rated will rated only. Okay, see, once again I will explain. So during starting, handle is moving from off to on position slowly. Whenever we move off to on position, step by step, stud by stud, armature current step by step limited, and field current also flowing in all resistor. Anyhow, at on position, this is the armature current, and field current is going in all resistors, and then come back like this. This is the field current. Now same field current is going in holding coil in this electromagnet also. Same field current is going in electromagnet holding coil. Now there is some strength of the magnet. Once you touch the stud was 6, the handle is attracted by magnet. Now it is in same position, attracted. Handle attracted by the magnet. Now it won't go back. If you leave the hand also, it won't go back because magnet is attracted. Now armature current is flowing in this direction and field current is going in back. So anyhow, motor starts rotating. So motor is started with a limited starting current. Now overload protection required. Overload means the rated current of this motor on the nameplate is 20 amps. Means 20 amps we can apply without any problem. Now I will fix the overload magnet here for 25 amperes because 22, 23 also we can operate, no problem. I will fix this magnet here. How to fix that magnet like that? Let us fix the magnet first. Then below that magnet I will place one iron rod. How to arrange for 25 ampere? Suppose I will place for 1 centimeter distance below that. For 1 centimeter, when there is a 20 amps itself, it is attracting. It should not attract. That's why what I will do is I will increase the distance, some 2 centimeters. Now at that 2 centimeters, I will check. During manufacturing we have to do all this. So at a 2 centimeter distance, when there is 25 amperes in the magnet, then only the rod is attracted. Okay, now it is fixed. So 2 centimeter I will fix. Like that I will fix the iron rod below that. Now at there, whenever 25 amps is drawn by the motor load current, then this magnet will attract the iron. Whenever iron is attracted, what happened? It will short these 2 points, AB. AB means holding coil terminals, that is. Now holding coil terminals shorted means no current will go in the coil inside. It will come like this directly. Okay. Now, what if there is no current in holding coil? What is the strength of magnet? No strength, zero. Because of no strength, there is a spring attached. The spring will take the handle to off position. Now, automatically handle come back to off position. So, motor is protected from overloads. Okay, clear now? Manually, if you want to off, just remove the supply. Okay. Yes. Spring, it is a spherical spring. When you move the handle, spring will tighten. When spring tighten is some force is acting in the spring now. So whenever there is no strength of the magnet, who will bring that handle to off position? The spring will make the handle to come back to off position because spring will become loose again. So then it will come back. Okay. Okay. Now we will come back to drawback of this. See the drawback of this 3-point starter. Field current, no problem, because what is the already field winding resistance RSH? Very high value, na, it is 150, 200 ohms like that. So we are adding the resistors in the range 5 ohms, 10 ohms like that. So it won't affect that much the field current. Okay, that's why if it is in series with field winding also, no problem. Okay. Now I will show you here itself in the previous concept. A DC shunt motor running at rated speed. If suddenly shunt field open circuited, what is the answer? If suddenly shunt field open circuited, what is the answer? No, previously given. What is the answer? Dangerous high speed, na, that is. Theoretically, what is the answer theoretically? Dangerous high speed. But practically what I said, it comes to stop. It comes to stop. Why it comes to stop? Observe now in starter. Suppose field winding gets open. Whenever field winding open, what is the field current? Zero. If field current zero, what is current in holding coil? That is also zero. If current in holding coil zero, what is the strength of magnet? Zero. If magnet strength is zero, spring will take the handle to off position. Then how motor will rotate? So there are two answers for that. Theoretically, practically. But you never confuse that, because in the examination you should not again uh, should not make me wrong. Like I said, theoretically and practically, that's why we confused. So every time in your answers, theoretically only you answer the questions. Dangerous high speed only correct. But I am giving some practical information. That's it. Practically, what is the speed? Comes to stop. Now clear na here how it comes to stop. When field open, field current zero. Current in holding coil also zero. Then strength of magnet becomes zero. Automatically handle comes back to off position by spring. Okay, clear it is, everyone? Okay. Today the people looks like mood off. Response is very less. Okay, no problem. I will adjust. Okay, 3-point I said already. 3 points are nothing but L, A, F. That's why we call 3-point starter. Okay, 3-point means L, F here. Line terminal, field terminal, armature terminal. That's why it is 3-point starter. Okay. Now let's see what is the drawback of this starter. The drawback of this starter is, observe here carefully. Observe, we have 3 speed control methods, mainly flux control, armature resistance control, voltage control. Now for flux control particularly, what we do for flux control, how to control flux in shunt motor? by adding a resistance in series with field winding. Whenever resistance added, field current decreases. Whenever field current decrease, flux in motor decrease, motor speed increases. Above rated speed we are getting. But there is a problem in this starter. What is the problem is observe here. Whenever field current is decreasing, same current is flowing in holding coil also or not? Yes. Now what is the strength of the holding magnet? Also decrease. Whenever field current is decreasing, the strength of holding magnet also decreases because same current is going in this also. Because of strength reduce, the handle automatically come back to off position because there is some spring force. Spring is trying to bring the handle off position. Now magnet is attracting that handle towards this. Whenever strength of magnet reduce, who will hold the handle here? No one can hold it. That's why the spring will bring the handle to off position. So this starter is not suitable for flux control method or field weakening method, we call it is. Field weakening or flux is reducing. So this method is not suitable for flux control or for high speed operations. This starter not suitable. Clear all of you this point? That's why we go to 4-point starter. Is it clear why it is not suitable for flux control? See, what is the field current? At the on position, field current will come like this in all the resistors, and then this is the path of field current. Field current is this. Field current going in the holding coil and then enters into field winding. This is the path of field current. Same current, field current is going in holding coil also. That's why when you add a resistor in the field winding, field current reduce, and same coil in the holding coil also same current is flowing. That's why strength of magnet also reduce. So whenever you are reducing the flux magnitude, at one instant the handle may come off position because strength of magnet reducing here. That's why it is not suitable for flux control method. Okay. Then we go to 4-point starter. So write 2 important points here. First, during this, I will give the variation of armature current and speed. This is also in previous engineering services and some competitive examinations we got same question. See here, variation of armature current and speed. Stud 1, stud 2, stud 3, 4, 5, 6. Total 6 studs we have. How the current and speed will vary? So little concentrate. So figure is little complex here. Try to understand properly. Handle is at off position initially. Now I will move the handle to first stud. Once I touch the handle to first stud, at that instant, what is the current? Maximum. See, at each and every stud, current will oscillate between two values, maximum and minimum, maximum and minimum. At each and every stud, like that we will design that resistors here. Like that we design. So how they will oscillate is, see, once you touch the handle at first stud, what is the armature current? Tell me. V minus back EMF 0 there at that time. Once you touch, divided by RA plus total resistance. Let total resistance R1 plus R2 plus R3 plus R4 plus R5. Total resistance. This current is the maximum current. See why maximum? I will tell. Just wait. This is at that instant it is maximum. Maximum is let this much current. This is the current. Now let us keep the handle at same stud. Keep the handle at same stud for 2-3 seconds. Now your current at same stud will decrease again. Why it will decrease? Once you touch the handle, at that instant it is maximum because EV is 0. But after that, when current is flowing slowly, Now torque is produced. Now motor starts rotating. Whenever speed of motor little increase, see initially current maximum, due to that the speed of motor now little increases. Whenever speed increase, back EMF also little increase. Then V minus EB, some back EMF will come. Not completely because little only speed increases. So based on that little back EMF divided by same resistance R1 up to R5, same resistors. Why current decreases? Because some back EMF induced. That's why at same stud 1 now as speed increases little, current little decreases. This is minimum current. Okay, this is at stud 1, first stud it is. Now let us move your handle to stud 2, off position for stud 1. Now let us move the handle to stud 2. Once you move the handle to stud 2, R1 is removed in the series with armature or not? Yes. Now IA will flow only from here, IA, and IA will not go in R1 now. Means some resistance you are removed. Whenever some resistance removed, what is the current? Resistance eliminated. Current now again boost up. Little current increase. What is that current now? V minus EB1 divided by RA plus R1 is not there. R2 plus R3 plus R4 plus R5 only. Because R1 removed, that's why current increases. So at stud 2, once you touch, again current goes to maximum value. Whenever current increase, little speed again increase. When speed increase, again current decrease. This process will continue at each and every stud. See, again current decrease. Let us move the handle from 2 to 3. Again current increase. Current increases. As current increases, again speed increases. As speed increasing little, again current decrease. Now let us move the handle from another stud. Because of resistance is removed, again current increases. Again speed increases. Like that current decrease. Again current increase. Speed increase. Again current decrease. Now as current is decreased, finally handle is its last stud it is. Now current is constant. So speed also constant. After that it won't change. So this is the variation of current and speed during starting of a starter. Variation of IA versus speed during starting. Clear all of you how we are getting that variation? All of you clear? Variation of armature current with speed at each and every stud, stud by stud, stud by stud, current varying like this. So this is called maximum current, this is called minimum current. In between these two limits, maximum value, minimum value, current will oscillate. So like that only we design starter. Based on this only we have the questions in the conventional calculation of these resistors. Okay, so only in the mains, during mains, again you have classes, those whoever will fall prelims ESC join. So there we will see calculation of these resistors also. Okay. Like that we design resistor. How it is going to same maximum is like that we design resistor values. That's what that is I'm saying. Okay. Now there is a drawback in 3-point starter. What is the drawback? It is not suitable for flux control. Now I will change the same starter to 4-point starter. Okay. So you try to take a screenshot of this because in the same diagram I will change 3-point to 4-point starter. Copy paste means it is Okay. See now 4-point starter. So this is 4-point starter. Now what we did here in 4-point starter, field current and current in holding coil I separated. Field current and current in holding coil, these two separated. This is current in holding coil now only. This is field current. From this point it will divide holding coil current, field current. Whenever you add a resistor, field current decrease, but no change in holding coil current. Holding coil current depends on this resistor value. Now you may get doubt why the resistor directly short. If you directly short, field winding directly short circuited, or voltage source also may get short circuit whenever the handle is at stud 1. See, completely dead short circuit it is. So to avoid that short circuit, we add some resistor R here in series with holding coil to maintain the holding coil current. So what is 4-point starter? Simply in this starter, the field current ISH and holding coil current are separated. Holding coil current are separated. Holding coil current are separated. So because of that, it is suitable for flux control also. This is suitable for flux control or high speed operations of motor. So right now it is not there in gate. Okay. So that is only difference 3.4 point, both almost same operations both. Completed. See this question. Yes, right. A 4-point starter is used to start and control speed of a shunt motor with armature. Why we use mainly 4-point starter? Because in 3-point starter, there is a problem of weakening flux control method. That is not suitable. But 4-point starter is suitable now for field control method. Particularly, we use 4-point starter. Option B only correct. Okay. Option B, flux control, it is suitable. Yes. 2-point starter for series motor. Okay. So this is about starter, brief about starter. Let's see about losses in DC machines. Losses. Yes, A also we can use armature resistance control also we can use, but mainly we are using 4-point starter for what purpose? Flux control only, no. Otherwise, we can go with resistance control means we can go for 3-point starter. And 4-point starter cost is more compared to that. That's why we don't use. Only for flux control method we use 4-point. Let's see losses in DC machine. What are the losses in every machine is what? Rotating machine. In transformer, we have seen the losses are mainly two types, mainly two majorly, iron loss and copper loss. So same losses will be there in every rotating machine. Same losses will be there in every rotating machine. Additionally, we have mechanical loss. Rotating machine is mechanical loss is must. Okay. Mechanical loss is must in rotating machines. Every rotating machine there is mechanical loss, but not in transformer because it's static device. So totally in DC machines, the losses we categorized as first, no load rotational loss. No load rotational loss we call, or simply rotational loss also you can call. Rotational loss. And here rotational loss W naught, it is the sum of a small iron loss plus mechanical loss. In DC machines particularly, we never talk about iron loss separately. Separately, we don't consider iron loss. Like in AC machines, in induction and synchronous machines, we have iron loss also separately. Iron loss also we need to take. But in DC machine, the iron loss is negligible loss. Small iron loss will be there. That is, we add with rotational loss itself. Separately, we never consider. Okay. Now, anyhow, the rotational loss of DC machine is variable loss or constant loss. It depends on speed mainly. If the speed is variable, loss is variable. If speed is constant, loss also constant. So if you take shunt and series motor, for example, what is the speed of shunt motor? Almost constant. Speed of shunt motor is constant. If the speed is almost constant, what is the mechanical or rotational loss of that motor? Constant loss it is. Or if you take series motor, what is the series motor speed? No load speed is dangerous, high speed. No load speed is dangerous, high speed. And full load speed is how much? Full load. Rated speeds. Rated speed means normal 1200, 1300, 1400 in that range. So this is called variable speed. This is dangerous means let some 5000 RPM. This is some 1400 RPM. How much variation? Thousands of RPM variation. That is called variable speed. But shunt motor, no load speed, full load speed, like induction motor, almost same. 40, 50 RPM will reduce. So that is we treat constant speed. So loss is constant for shunt motor, variable for series motor. Okay. This is one loss. Next, second loss is ohmic loss. This is common everywhere due to resistance of winding it is. It is due to resistance of windings. What are the windings we have? Mainly two windings. If you take shunt motor, armature copper loss, Ia square Ra plus field copper loss, ISH square RSH. Now, this ohmic loss is variable loss or constant loss. Actually, it is variable because it depends on current. Whenever current changes, loss will change. But in case of shunt motor, Ia square Ra only variable loss, and ISH square RSH will come under constant loss, because what is the field current of shunt motor? Always constant. Resistance anyhow constant. Then I square R also constant. So field copper loss is constant loss for shunt motor. Only armature loss is variable. Okay, that you have to take care what type of motor we are using, shunt or series or compound. Based on that, that field copper loss will change. So this is our second loss. These two only mainly we consider in our calculation, but additionally there is a stray loss. Third one is stray load loss. Stray load loss. Generally we neglect this. Generally we neglect stray load loss. We neglect. It is a small loss, and this loss is mainly due to cross magnetizing effect of armature reaction. This loss is mainly due to cross magnetizing effect. That is due to armature reaction. One of the effect is what? Cross magnetizing effect. Due to that, the distortion of main flux. What is happened to main flux? Distorted. Main flux is distorted. Whenever main flux is distorted, the flux lines, see, previously we have seen stator, rotor. And is it only there in the machine? Only stator, rotor? No. Inside the machine, we also have commutator. Same commutator is connected to shaft. Commutator made up of copper. Now the flux lines will touch with commutator or not? Yes, definitely it will touch, because inside only that is. So whenever flux line interact with commutator surface, definitely in the commutator there will be circulating currents, and that is we consider as one of the stray loss. Inside the machine we have bearings. The flux lines, magnetic energy, it may spread throughout the machine. So due to that flux lines, there is some influx linkages with bearings of the machine. Now bearing also made up of steel. Now in that also there is some conducting it is. So due to that some currents will flow in the bearing body also. So due to all this, wherever additional losses other than iron loss, mechanical loss, I square R loss, in other than these, wherever the losses will take place, that is all we consider as a stray loss of machine. Stray load loss. Now this is generally small one, minor loss it is. Generally we neglect. If it is given in the numerical, we will consider. If not given, we will neglect. We don't consider. If given, you take in the question. If not given, neglect this. How to find stray loss? Important question. How to find stray load loss? Suppose you want to calculate I square R loss, you can find. No load rotational loss also you can find. Mechanical loss. How to find stray loss? There is one test for this, that is retardation test, also called running down test. So using that retardation test or running down test, we will calculate stray load loss. Okay, if it is required, it is for large DC machines, we use this one, retardation test, to find the stray load loss of machine. Generally for small size, we neglect this loss. Okay. See, no load rotational loss we can find by conducting some test. We have one no load test, Swinburne's test we call. By conducting that, we can find this. How to find ohmic loss? Current we know, calculation. Current you can calculate, and our resistance of armature, resistance of field winding, you have to measure by using some measurement technique. Low resistance measurement, medium resistance measurement. So use that and try to find the resistance values. Okay. Now let's see efficiency of DC machine. Efficiency. Efficiency of DC machine. Both generator and motor we take simultaneously. First, generator efficiency. See, for this efficiency equations, you never see any textbook, because if you see Bimbra also, he will confuse you like anything. You cannot understand or you cannot remember any equation in that. Okay, because he will write output is input minus losses, input is output plus losses. So different ways he will write, he will take. So they are all confused. So better is remember like this. That is, if you want efficiency of generator, what is the output of efficiency? Means output by input power. What is generator output? Electrical. What is generator input? Mechanical. So it is the ratio of electrical output to the mechanical input. Okay. Now, as we are electrical engineers, we are best in electrical quantities rather than mechanical quantities. That's why what we do is we will convert the complete equation into electrical. Whether it is generator or motor, anything, you convert the complete equation into electrical quantities only. That is output by input. What is electrical in this? Output. That's why change the input power. Output by input we can write as output plus losses. Now this complete equation in electrical form only. Output electrical, losses also electrical, and mechanical loss also there. Okay. So mainly this output, both electrical we converted. Consider a shunt generator. Example, shunt generator. Now in this shunt generator, if you connect a load, terminal voltage VL, current IL, IA, ISH, RSH, RA. What is the output of generator? Tell me. Output power. Output equal to voltage across load VL into IL. Therefore, the efficiency of generator is output VLIL divided by output VLIL plus losses. What are the losses? Mainly I said two losses. One is no load rotational loss plus I square R losses. Armature copper loss plus field copper loss, ISH square RSH. So this is efficiency of generator equation. Okay. And don't write again, it is like converting here. Somebody will take input minus losses. So don't write this many equations. Convert the equation simply into electrical powers. Now, efficiency wise, what is required? Maximum required. Let's find what is the condition for maximum efficiency. Same condition whatever you know in transformers and also in alternators. For generators or transformers anywhere, condition for maximum efficiency is what? Variable loss equal to constant loss. Variable loss equal to constant loss. That is the condition, right? Condition for maximum efficiency. Condition for maximum efficiency. So how to find maximum condition? Differentiate the efficiency with respect to current IA equating to 0. So if you differentiate, IL means IA minus ISH. This is IL. So in the numerator we have IA, denominator also there is IA. So if you differentiate, the final condition I'm writing, you will get variable loss equals to constant loss. Variable loss equal to constant loss. See, this is one of the engineering services prelims question. In the condition options they given, like see how it is. The condition for maximum efficiency of generator. Options are variable loss equal to constant loss. Second option is constant loss equals to variable loss. Actually, these two meaning same or not? Yes, these two are same meaning. But what is the answer here? variable loss must be equal to constant loss. Constant loss is never equal to variable loss. That is a constant, fixed that is. That's why variable loss, this is only correct. So simply the total loss at maximum efficiency. What is the total loss? 2 times of constant loss, because constant loss plus variable loss. At maximum efficiency, variable loss equated to constant loss. So 2 times of constant loss you get, or double the constant loss. This is the total loss at maximum efficiency. If you get any question from this condition, only number of times we got question in previous examinations. Variable loss equal to constant loss. So we will see some questions also how to get. What is variable loss for shunt generator? Tell me. Variable loss for shunt generator, IA square RA only variable. What are the constant loss for shunt? Rotational loss constant, and ISH square RSH also constant. Okay. So from this condition, we have the questions. Calculate the armature current at maximum efficiency. Like this type of questions we get. Okay. Let's see for motor efficiency. Same condition for motor also. Motor or generator, same condition for maximum. Variable loss equal to constant loss. Remember this. Let's see now. Motor efficiency. Efficiency of motor. What is the motor case? Output power by input power. But motor, what is output power? Mechanical. Input power, electrical. So mechanical output to the electrical input. Simply we can write output by input. What is electrical power here? Input. So convert the complete equation into input only. Output power we can write as input minus losses divided by input. Okay. Complete equation first convert into electrical. That's it. Now, if it is a shunt motor, example, shunt motor taken. IL, IA, ISH. Now, what is the input of motor? Efficiency of motor equal to input power is V into IL is the input minus losses. What are the losses? Same losses, generator or motor. Rotational loss, armature copper loss plus field copper loss divided by input power VIL. This is efficiency of generator. Motor. Efficiency of motor. What is condition for maximum efficiency? Same condition. Remember, variable loss equal to constant loss. Stray loss, we cannot say it is variable or constant. Actually, that loss is depends on armature reaction. So that is a variable loss only, because load variation will be there. Whenever load changes, cross magnetizing effect will change. So that is variable loss. Let's see some questions on this. See the question. So it is a general question, not related to efficiency calculations. Torque question it is. We need to calculate output torque of the motor. First read the question with patience. A DC motor has the following specifications. 10 HP. What is 10 HP? It is the rated output power. It is the mechanical output or net output of motor. It is mechanical power. 230 volts. Flux per pole 0.01. Number of poles 4. Number of conductors 666. Number of parallel paths 2. Armature resistance 0.267 ohms. The armature reaction negligible and rotational loss given. Mechanical loss or rotational loss, nothing but 600 watts. The motor operates from 230 volt supply. If the motor runs at 1000 rpm, the output torque of motor is dash. Output torque of motor is dash. See, output torque means what? If it is a motor, for example, already given it is. This is the shaft of motor. This is motor input, electrical. Motor output is two types again: gross output, net output. Whatever we are collecting the shaft, what is that output power we call? This is net output power, or simply we call output of motor, that is only. And actually in the rotor, whenever rotor starts rotating, this is the gross mechanical power. Gross. What is the P gross equation? We have already mechanical power developed in motor is EBIA. And if you want net mechanical power, how to get net or output of motor? From the gross power, you need to remove mechanical loss. That mechanical loss given 600 watts. How to find gross? EB value required. EB required first. That EB you can find using this data. EB equals to, now some of the people will get doubt. So already there is a 10 HP here, output power. Then torque equal to that output power by omega. Then if you substitute, you will get the answer. Omega is 2 pi n by 60, n also there. Then why cannot we use this equation? You can use this, but is it mentioned in the question it is operating at full load? Is it mentioned? If it is given motor is running at 1000 rpm at full load condition, then you can use 10 HP directly. That is full load power. 10 HP is the full load, but it is not given anywhere. That's why you should not use that equation directly. So calculate as usual gross power EBIA. First EB you will get Z phi n P by 60. Z is 666, phi 0.01, n 1000 rpm, number of poles 4, 60 A value given 2. What is EB? Calculate first. EB. Tell me, what is the value of back EMF? Yes, very good. Triple two also. Okay. EB is 222. If EB is 222, how to find IA now? Can you take that IA here? See, they given a current, I think. Current given? Yes, 37.5. So do you take that current IA directly? No, that 37.5 is the full load current. So you should not take that current. Then how to find IA? Yes, you can find IA because there is a supply voltage, there is a back EMF. V minus EB by RA also given in the question. That's why use that 230 minus 222 by armature resistance 0.267. What is the IA value? Tell me. IA how much? Yes, approximately 30 amperes, right? 30 amps you get approximately. IA is 30. If IA is 30, calculate the gross power, P gross. EBIA. EB into IA. EB is 222, 30. This is 6660 watts. This is the gross power. Next, therefore, the net mechanical power equal to gross minus mechanical loss. Gross is 6660, mechanical loss 600, I think. 600, right? Now, what is this value? 6060 watts. This is the output power. Therefore, output torque is that output power divided by omega. That output power divided by omega. 6060 divided by 2 pi n. N is given 1000 rpm divided by 60. Calculate the output torque. Calculate this, how much? 57.79 Newton meters. So this is the answer. Okay. All of you got it? Next question. Next. See this one. Get 16, 2 marks question it is. Yes, no problem. 57.7 or 7, 8, 8, I think anything. Right on. A DC shunt generator delivers 45 amps at a terminal voltage of 220 volts. The armature and shunt field resistances are 0.01 ohm and 44 ohm respectively. The stray losses are 375 watts. The percentage efficiency. See, in this question, they did not given any rotational loss like that. Given as stray losses. So you take that is only and don't think very much about that. Whatever is given, you substitute. Whatever is not given, you also leave that. Don't think that it is not given, how can we solve? Whatever is available, substitute. First, draw the figure. A shunt generator delivers 45 amperes. 45. Load current is 45 it is. At a terminal voltage of 220 volts. Armature resistance 0.01. Field resistance 44. What is the field current? ISH equal to V by RSH. 220 by 44. How much it is? 5 amperes. Then armature current is sum of the two currents, IL and ISH. Therefore, 50 amperes is armature current. Then what is EG? EMF induced. EG you can find. Otherwise, not required EG also, because efficiency of generator we need to calculate. What is the formula? Output power VIL divided by output power plus losses. What are the losses? IA square RA plus ISH square RSH plus rotational loss. But that is not given. In that case, stray loss given. So you substitute that stray loss only. Stray loss or stray load both are same. What is V here? 220. IL is 45. 220 into 45 plus IA square 50 square into armature resistance 0.01 plus ISH 5 square into 44 plus stray loss is given 375. Find out the answer, you will get how much it is. Yes, 86.8 percentage. Check it is correctly. 86.84, right? 86.84 percentage. That is correct. 86.9 means check, take exactly decimal points. 86.8 will come exactly 86.84 percentage. Check it once. Yes, 86.84, correct. Completed. Next question. See this question. A 250-volt shunt generator delivers 190 amps with a field resistance of 125 ohm and stray loss of 800 watts. First question. The armature resistance of the machine with a full load efficiency of 90% is dash. Given. First draw the figure. Figures only important. A 250-volt shunt generator delivers 190 amperes. Means load current is 190. 250 volts is the terminal voltage. And field resistance 125. Then ISH is how much? V by RSH 2 amperes. Then IA how much? 192 amperes. Okay. Given stray loss is 800. We have to find armature resistance that is not given such that full load efficiency 95%. First question. Given full load efficiency 90%. Now what is the formula? 0.9 equals to efficiency of generator is what? Output power 250 into IL. IL is load current 190 divided by 250 into 190 plus IA square RA. Let us keep IA square RA as it is because we need to find RA value unknown plus ISH square RSH is 2 square into 125 plus given other loss is 800. Substitute here whatever is given. Now solve this equation. You will get IA square RA value first. Tell me what is IA square RA value from this. IA square RA. Yes, in series motor, shunt field copper loss also variable because same current is flowing no armature current. Tell me this IA square RA how much? IA square RA 3977. Okay, 3977 or 4977. Check it. Yes, 3977. Right. 3977.7 watts. Here IA we know already 192 square into RA equal to this. Calculate RA value from this. What is RA? Take up to 3 digits exactly you will get 0.107, right? 0.107 ohms. So RA value is 0.107. This is first question. Now what is second question? Armature current at maximum efficiency is dash. Armature current at maximum efficiency. At maximum efficiency. At maximum efficiency condition is what? Variable loss equals to constant loss. What is variable loss? In shunt generator, IA square RA equals to constant losses ISH square RSH plus rotational loss, and whatever is given, stray loss is given, substitute that is only, because we have to take whatever given other than this. These are all constant losses only because they are not changing. Changing is we cannot find that variation. That's why whatever given other than that IA square RA remaining all constant only in shunt. So taken it is. Now IA we need to find IA square. RA is how much? 0.107. ISH square how much? ISH square 2 square into 125 plus stray loss given 800. Solve this equation, calculate IA from this. Find out IA. Yes, 110 amperes. Find out IA. So don't give this IA because 192 previous case, full load case that is. But we need to find current at maximum efficiency. That's why condition we are applying. Apply this condition. Don't substitute IA 92 here. And this is IA unknown for us with respect to this condition. How much IA no? Calculate IA from this equation. Yes, 110 amperes you will get. 110 amperes. This is the armature current at maximum efficiency. From the condition we have to find. Okay, so around 110 amperes. Take 0.107. So don't take because that conditions are different. That is for maximum power output. Maximum power output condition. What is the condition for maximum power output? EB equals to V by 2. So these are different. Don't use these relations. And efficiency at that maximum power output is 50%. So don't use that concept. That is different. For power output relation only that is, not efficiency relation. Don't use that. Losses. This is with respect to losses. Next question. Why we are using RA value 0.107? Because RA is fixed value, no? RA once you got that value never change. Okay. Yes. Next question. Answer this question. A 200 volt DC shunt motor delivers a output of 17 kilowatt with an input of 20 kilowatt. Input given, output given. What is losses? Input minus output. Input minus output. What is input? 20 kilowatt. What is output? 17 kilowatt. What is losses? 3 kilowatt. That is 3000 watts is the loss. But what is question? Question is what? The field winding resistance given, armature resistance given. Maximum efficiency will be obtained when the total armature copper loss. See, at maximum efficiency, condition is what? Armature variable loss, IS square RA equals to constant loss. What is the constant loss? ISH square RSH plus rotational loss. ISH square RSH plus rotational loss. How to find that? How to find it? Tell me. This total 3000 watts, whatever we get, what is that? This is equal to all the losses. What are the losses? IS square RA plus ISH square RSH plus rotational loss. Rotational loss. This is equal to 3000. Now from this, calculate what is the constant loss. What is constant loss from this? Calculate that. ISH square RSH plus rotational loss is commonly we call constant loss. That is equal to 3000 minus IS square RA. That is 3000 minus IS square. What is IA? You need to draw the figure. A DC shunt motor. A 200 volt DC shunt motor. Input power 20 kilowatts. Input 20 means what is the load current? Tell me. IL is how much? 20 kilowatts is power. 20 K by 200. How much current? Load current? Load current 100 amperes. Yes, 100 amperes. Field resistance given 50 ohms. Then V by RSH ISH equal to 4 amperes. V by RSH 200 by 50. Then IA equal to 96 amperes. So IA we got 96 square into armature resistance given in the question 0.04. Calculate the constant loss value from this first. Calculate the constant loss. Directly also IA square RA you can find anything from the figure IA square RA. Calculate only IA square RA. That is also correct. What is answer? Tell me. What is this value? 2632, right? This is 2632 watts. ISA square RSH plus W naught. This is itself IA square RA, no? Condition for maximum efficiency what? The constant loss equals to this is the constant loss. Condition for maximum efficiency is this. The IA square RA equals to constant loss. What is the constant loss we got? This one, 2632. That is only the answer. From the losses, we calculated constant loss. Constant loss. According to maximum efficiency, IA square RE must be equal to constant loss now. What is the 2632? Answer is 2632. Okay. Clear? Total losses we have 3000. Total losses are what? IA square RA plus ISA square RSH plus rotational loss. From that, we calculated constant loss, sum of these two, 2632. At condition for maximum efficiency, IA square RA equal to constant loss. That is I taken. Okay. How ISH 4 ampere, V by RSH 200 by 50. Okay. Next question. Answer this question quickly. We take break. What is answer? The maximum efficiency occurs in a separately excited DC generator when the terminal voltage and the induced EMF, the stray losses if the armature resistance is. There are some questions, how they given, it is only that fellow, whoever will create the question, he only knows whatever he is thinking. Okay, accordingly we have to understand. See how much difficult for us. Given EG 240, given terminal voltage 220, given armature resistance 0.2. From this we can find IA only, that is EG minus V by RA. EG 240 minus 220 by RA 0.2. What is that value? 20 by 0.2 means how much? 100 amperes. We need to find stray losses. Stray losses means how can we find? Only one loss we can find in this question. What is that? IA square RA we can able to find. No other loss. That is IA square RA, 100 square into RA how much? 0.2. 100 square, 10,000 into 0.2. Nothing but 2000 watts. This is only you can find in this question. Can you find any other loss? See the fellows how giving. Stray loss. We have to understand, so much struggle for us. So maximum efficiency condition IA square equal to IA square RA equal to constant loss. But here they said the stray losses if the armature resistance will be dashed. Yes. That means IA square RA we have to find in this, but given like that. Okay. Okay. So take a break. So after break, we see about tests of DC machines. So what are the tests? All tests we will see briefly once. Okay. Test is only for ESC, not for gate. Did not mention any other loss. That's why only one loss we can calculate and check whatever the options satisfy. So no need to leave. That is your wish. You can listen tests also. Okay. Take a break. Yes, losses efficiency is there in gate. Test is not there in gate. Parallel operation also not there. So that you refer in textbooks, not required, not important that is. For state government exams, each and every topic is there. Okay, each and every topic. Just like engineering services syllabus for state government exams. Yes. Yes, total power means IA square RV. Take break. So mostly 1 hour will take. After break, we complete this test of DC machine. Okay. So if it is air core also, flux is linking with body, and our body is not a good conductor, no? Current if directly touch, then it will flow for some time due to resistance of the body, but because of the flux EMF induced, that is a rare, less chances to get EMF and induced and current. That's why we don't get any shots. And no idea on that clearly. Okay, see, the tests on DC machines are mainly, we have direct test. This is also called brake test. This is also called load test. Next, indirect test. Indirect, this is also called Swinburne's test. Swinburne's test. Next, third, Hopkinson test. Hopkinson's test. This is also called regenerative test. After that, field test. After that, lastly, retardation test. See, in each and every test here, except retardation test, in all these 4 tests, we will calculate efficiency of the machine, motor. Efficiency of motors, we calculate. Efficiency of the machines, motor or generator, anything. Okay. But in the 5th one, retardation test, we don't find efficiency. The main purpose of this test is what? To find stray loss. To find stray loss, we conduct this test. And out of this, the test information you should know well to answer some questions directly, like field test. For which motor we use field test? Only for series motor. Series motors is also called traction motor, because in traction we use series motors mainly. That's why this is also called traction motor. Okay. Now this is a no load test. Swinburne's test is a no load test. As it is no load test, this test is not suitable for series motor. It is not suitable for series. See, out of these 5 tests, series motor suitable is first one and fourth one. 1 and 4 only suitable for series motor. Direct test or brake test, directly load applied, load test it is, so suitable for series. And field test is for only particularly series motor. Remaining are not suitable for series. In remaining mode tests, we can use shunt motor, compound motors, but series motor, only these 2 are suitable. Okay, because no load test we cannot use for series motor. If you use series motor no load, what happened? Dangerous high speed it rotates. So it is not suitable for series motor. No load test not suitable. Okay. Right, the first one, direct test. Direct, why we call direct is, directly we apply a load on the motors and directly we calculate efficiency. Okay, so here we don't see any questions, only the procedures we see here. For each and every test, the procedures and important points in each test. Numericals you never get in prelims or prelims also. Only in the mains examination you will get numericals on this test. So there is one question like previously in the Hopkinson test they given. So that question will take minimum 10 to 15 minutes. So that type of questions we will get in mains conventional examination. In objective type, you never get any numerical question on this test. But you should know the complete information about tests for objective also. Right. First one, direct test. Direct test. This is also called brake test. Brake test. Direct test or brake test. Now, as it is brake test, it is suitable for every motor. Now, let us take, so I'm considering a shunt motor. Considering a shunt motor, take the figure. So this is your lab test. So however you did in the lab, the same experiment now you have to remember, recollect it is just brake test. In the labs we do this. So this is a brake drum having radius small r, where small r is the radius of brake drum. Radius of brake drum it is. And this is brake drum. Wherever we apply, that is called brake drum, it is using belt. This is the belt. And these are called spring balances. It will measure how much weight you applied in kgs, kilograms. These are called spring balances. Okay. See the procedure of this. So you need to apply directly load. So first apply rated voltage to motor. Rated voltage, apply rated voltage. Now it will draw current IA, ISH. Now motor starts rotating. Let us adjust the rheostats here such that motor should rotate at rated speed, whatever given on the nameplate. Tachometer, we can adjust the speeds by changing these rheostats. Armature resistance control, flux control. So based on the speed we can adjust, you will get the rated speed of the motor. Once it is rated speed, now start applying load here. Let us apply load. Rotate this. If you rotate, the belt will get tightened. Belt is tightly attached to the brake drum. Then the spring balances will give some readings here. S1, S2 in kgs. Now we have to calculate torque. How much torque is produced? What is the torque formula? Torque formula, if you remember in the labs, we use 9.81 into S1 minus S2 into radius of brake drum, R. This equation we use to find the torque produced on the brake drum. 9.81 S1 minus S2 is this spring balance weights into R is radius of the brake drum. Okay, using this equation torque we calculate. So the tabular column we need to take is first supply voltage. Anyhow this voltage is fixed. Okay, after that this load current drawn by motor. So step by step we apply load. First 2 amps load, that after that 5 amps, 7, 8, 10, like that. Step by step we increase the load, brake we apply. If rated current is 20 amps, up to 20 we apply the brake. Up to 20 by measuring this current from the ammeter. Load current and S1, S2 readings. After that torque value and then speed. From that you will get output power. From that you will get input power. From that you will get efficiency. So this is a tabular column you need to take. So let us take some load current first, 2 ampere. There is some S1, S2 readings, measure that S1, S2 and calculate torque using this equation. And then speed using tachometer, measure the speed. Then output power. How to find output power? Output torque into omega, 2 pi nt by 60. N is there, T is there, and output power you will get 2 pi nt by 60. Output power we get. After that, input power. What is input power? Input V into IL. So you are calculating V is fixed. IL we will change step by step. So V into IL. Input. Now output is there. Input is there. Calculate efficiency. Output power by input power. You will get efficiency of motor in each step. Like that, apply load, calculate efficiency. Apply load, calculate efficiency. Up to what we have to do this procedure? Up to rated current of motor. So directly load applying, directly efficiency calculated. That's why we call direct test. Or brake, brake is applying. Or load, because load is directly applied. Okay. So this is about brake test. But here there is some disadvantages. What is the disadvantages is, if you remember in your labs, while conducting this test, we used to pour water in this, water in the brake drum. We used to pour water. What is the purpose of that water? Whenever belt is becoming tightened with the drum, it will get heated up. Brake drums heated up. If you don't reduce the heat, the brake drum also may get damaged. It will get problem. Okay, it will get break completely if it is overheated. That's why we need to reduce the heat in this. To reduce that water we use, and that water will circulate in that. Okay, and the main problem here is the total output power in this method you are wasting. The total output power is wasted in the form of heat. The total output power is wasted in the form of heat here. Heat only, na, that is friction. When you apply tightly brake, there is a friction between drum and the belt that is heated up. So total output power you are wasting. That's why this method or this test is not suitable for large size or high rating DC motors. For small rating DC motors, you can use that, but not for large rating, because large rating is more power output, more power loss. That's why only for small size DC motors it is suitable. Okay. And one more problem of this test is the spring balances. So did you observe in your lab spring balances? Spring balance. Actually, it has to rotate smoothly the pointer whenever load increase. But if you remember in your lab, the spring balance will oscillate continuously like this. They are rotating. When they are rotating itself, they will oscillate. They cannot show a standstill reading. The pointers will not give a stationary reading. So all of you observe now, this is the spring balances continuously oscillate like this. Then how you take in readings in your lab? Then you will observe very carefully that pointer, and you will take the center of the pointer based on the oscillation. Center point you approximately takes. Now why the spring balances are oscillating here? Because of vibration produced in the belt. Why vibration? Drum is attached to the belt. Due to that, belt will vibrate. Because of the vibration, the spring balance continuously oscillates. They cannot show a stationary reading. Don't say that in my lab pointer is showing stationary reading. Stationary reading is that pointer is dead. That is not alive. That's why it is showing stationary. Otherwise, if it is properly working, it has to show that oscillating reading only. Otherwise, not possible. Okay. Mostly in 90% of engineering colleges, the pointers will not work properly. They will stuck. They will stuck. Approximately, we take the reading and we do the calculation every time. Otherwise, if calculations are not coming, readings are not coming, take the previous values. That's it. Over. Okay. So this is a brief information about brake test. But if you conduct series motor brake test, you need to take care. What is the care? Whenever it is a series motor, before giving supply to motor, you should apply some brake on the motor first. You should apply some load on the motor. Under no load, never start series motor. It will go dangerous high speed. It will damage your motor. For that reason, before giving supply to series motor, you need to apply some brake tightly on this. Some brake, little brake, so that some load is there. Then you can give supply. So under load condition, no problem. It will start normally at low speeds. Okay. Next, this is the first one, direct test or brake test. These are the calculations in this. Output, first torque calculation, output power, and then input power, and then efficiency for each step. You will get directly efficiency in this. That's why direct test. Now second one is indirect test. Indirect. Why indirect is, we don't apply any load directly. Still we will find efficiency using equation. Using equation, we will assume, we will calculate. Now write that. Second one, indirect test or Swinburne's test we call. It is invented by Swinburne's. Swinburne's test. So the main purpose of this test, this is only the questions you get. The main purpose of this test is to find rotational loss of motor. Rotational or mechanical loss of motor. Because if you see the efficiency equation, output by, if it is motor, no? How we write for motor, efficiency of motor? Output by input. What is the known quantity in motor? Input, electrical. That's why convert output to input. Input minus losses divided by input power. What is input of motor? VIL minus losses in motor, IA square RA plus ISH square RSH plus rotational loss divided by input power. Input power, VIL. Now you observe this equation. Tell me what is unknown value for us in this equation. What is unknown, which we cannot find directly from the motor? What is that? Current we can find because rated current will be there on the motor. If you know the field current, you can find armature current also. So like that IA square RA you can find, ISH square RSH also you can find without operating motor. But without operating motor, you cannot know the rotational loss. You don't know that. That rotational loss we will find in this test. And what is the rotational loss of shunt motor? Constant. So if you find once that mechanical loss, that is constant for any load condition. Okay, that's why we will calculate that and we will apply load indirectly. Means we don't apply any load on motor directly. We will assume IL is some 10 amperes. Then what is IA in motor? IL minus ISH. We will calculate IA. We will substitute here. And again, we will take IL equal to some 12 amperes. Consider IL equals to some 14 or 12 amperes. 14. Now IL minus ISH. ISH anyhow fixed and IA we get substitute here. In every case, rotational loss is same we take. Now we will get efficiency in each and every case. Each and every assumption you will get efficiency. That is indirect efficiency. Directly we are not applying load. Still we are finding efficiency using this equation by knowing the value of rotational loss, which is calculated from Swinburne's test. Okay, so what is the main purpose of this Swinburne's test? To find rotational loss or one of the constant loss. It is constant loss of shunt motor. So Swinburne's test is a no load test. We don't apply any load. Under no load we operate. That's why it is a no load test. So as it is no load, is it suitable for series motor? No, not suitable for series. Only for shunt motor it is. Now let us consider a shunt motor. Consider a shunt motor. Considering a shunt motor, apply rated voltage to the motor. and drawing a current, load current IL, because it is a no load, the current run by motor we call IL naught. IL naught means no load current. IA naught, this is ISH. ISH anyhow constant always. The procedure is apply rated voltage to motor and then adjust the rheostats here, armature resistance rheostat or field rheostat, anyone, so that your motor should rotate at rated speed whatever given on the nameplate. Nameplate you will have speed. That speed you have to bring here. Once it is rated speed, put a ammeter here and measure this ammeter current IL naught. Okay. The only one reading we take. Apply rated voltage, adjust the rheostats. The motor should rotate at rated speed. Then take the readings of this ammeter. Enough. Therefore, under no load condition, what is the power drawn by motor? Input power. Power drawn by motor is V into IL naught. That input power equal to losses or not? Actually, input equal to output plus losses. But no load means, is there any output power are you getting? No, just motor is running. There is no output. That's why output is 0. But whatever input power is drawn by motor, that is equal to losses. What are the losses? That V into IL naught equal to losses. What are the losses in motor? Oh, what are the losses? Rotational loss, because it is rotating now. Rotational loss plus a small copper loss, IA naught square RE, plus field copper loss, ISH square RSH. Which loss we need to find here? Rotational loss. So from this equation, calculate W naught equal to VIL naught. That is voltage into current reading minus IN naught square into RA. We can find this. IN naught is what? IL naught minus ISH minus ISH square RSH. Field copper loss. This is also we can find. So you will get from this the no load rotational loss of motor. Okay, so you will get no load rotational loss. See, the procedure is apply rated voltage to shunt motor under no load, and adjust the speed to rated speed. Then take the reading of IL naught. Therefore, the power drawn by motor is equal to losses. That is, the power drawn by motor is VIL naught. That is equal to losses. What are the losses? This one. From this we calculated rotational loss. Whatever the rotational loss you will get, that is the constant loss of shunt motor. Now, using this equation, substitute that W naught here. Using these equations, calculate efficiency in each step. This is called indirect calculation of efficiency, not direct. We are not applying any load. Still, we can find efficiency. That's why it is indirect test. Okay, clear? Yes, rotational loss includes iron and mechanical loss, but iron loss we never talk in DC. That's why it is taking as mechanical loss. Remember, this test is not suitable for series motor because no load test it is. This is a no load test. Clear, all of you? Next, the third one is Hopkinson test, or called regenerative test. Third one, Hopkinson's test. Regenerative test. So this is little important than previous test. See, it is the name of the scientist Hopkinson who invented this, and in this test he taken two identical shunt machines. Two identical shunt machines he taken, and both are mechanically coupled and electrically also coupled. Two identical shunt machines in which both mechanically and electrically coupled. The two machines are mechanically coupled and electrically also coupled. So you will see the diagram, both mechanically and electrically coupled. Both mechanically and electrically coupled. See the figure. Draw the figure simultaneously. Draw the figure. So each and every figure, whenever asked to you, you should draw like that. You should prepare. See, both are mechanically coupled, electrically also coupled again. But switch is initially open condition. So in between, by changing the field currents, we will close the switch by observing that voltmeter. First take the figure. Complete the figure first. Just almost 15 to 20 minutes we complete. So now field test and retardation test. That's it. So first listen this. Completed all of you. So never ever sleep up to you get a good gate rank. Yes, so tomorrow you have schedule update also. That is tomorrow 7 a.m. to 10 a.m. you will have networks, and evening 5 p.m. to 9 p.m. you will have whatever most of yours EMF. Okay, note down this tomorrow schedule. Listen this. See, this is a shunt motor. The first one is here shunt motor. It is a shunt generator. Okay. Shunt motor, shunt generator. Two shunt machines. One is motor, other one is generator. See, initially switch open. We don't close. So try to understand. Little important it is. Observe here. First, under switch open condition, give rated voltage to motor. This one. Rated voltage to motor. Now motor starts rotating. Whenever motor is rotating, at the same speed generator also rotates because both are mechanically coupled. So speed of motor and speed of generator are same, equal. Now whenever motor is rotating, an EMF induced in motor, what is that motor EMF? We call back EMF, EB. And EMF induced in generator we call EG. EB proportional to N5, EG also proportional to N5. No change in that. EB proportional to N5. EG also proportional to N5. Now, if the supply voltage is like 240 volts, what is the back EMF generally? Less than that. Now, let us take the back EMF, for example, EB equals to 230. For example, 230 EB. Now, considering initially field currents of both motor and generator, I am considering same. ISHM equal to ISHG. Motor field current, generator field current, both are equal. If both are equal, flux of motor, flux of generator also same. Speeds are same, flux also same. Now what is EMF EG? That is also 231 because same machines, same speed, same flux, same EMF will induce 230, 230. Now tell me what is the voltage at this point? If it is 240, what is the voltage here? 240 only. What is the voltage here? 240 only. But as EG is 230 induced, what is the voltage here? 230 only will come. Then what is the voltmeter reading? Here 240, here 230. Difference is 10 volts will read. So you should not close the switch. When we have to close the switch? Whenever the voltmeter is zero reading, then only we have to close the switch. How to get zero reading? Here you need 240 volts. How to get 240? EG 230 because same field currents we taken. So then you are getting 230. But if you generate 240 here, voltmeter will read 0. For that, what we have to do? Flux in generator, we have to increase this. Because speed you cannot change. That is the motor speed. Both will change. That's why flux in generator you have to increase. Therefore, let us increase the generator field current than motor field current. If it is there, flux in generator increase. Whenever 5G increase, your EG increases. Now let us consider the EMF induced is 240 at a particular value of field current. If EG 240, then here 240. 240, 240, voltmeter reading 0. Once voltmeter reading is 0, close the switch. So before closing first, or don't close because you will get again confused. Switch open initially. Whenever switch open, this I and IAM same or not? I equal to IAM only, same current it is. Okay, clear all of this? Switch open, IAM both are same. If IAM is 10, I also 10. Okay, now I will close the switch because I equated 240 240 by changing the field current like that. ISHG greater than ISHM. This is one important question in this. That is, in this test, what is the relation between generator and motor field current? Both are equal. Are ISHG greater than ISHM or ISHG less than ISHM? Which one is correct? This is correct. Then only voltmeter will show 0 reading. Whenever voltmeter is 0, close the switch because both at same potential. Close the switch. Whenever switch is closed, now there is a current coming from generator because EG now greater than EG 240. This is 230. Now as this voltage greater, generator armature will supply current. Now a current IAG is coming. Generator will supply a current to motor. If IAG is supplying, then I will reduce or not? Yes. Current taken from supply will reduce. Previously, when switch open, I equals to IAM. But whenever switch is closed, IAM is sum of IAG plus I. But as IAG is coming from generator, no, this value of I will reduces. Now, a small current I is taken from the supply. From the supply, whatever current is taking, that will reduce because generator is supplying electrical power to motor. Motor is supplying mechanical input to generator. Now, these two armatures are exchanging their power. Output of generator is input to motor. Output of motor is input to generator. They are exchanging output, input, output, input, output, input. That is called regeneration takes place. That is regeneration. Power regenerated here. When power regenerated? After closing the switch. When switch we need to close? By adjusting the voltmeter reading to 0. When voltmeter will read 0? Whenever this condition is satisfied. At a particular value of that condition, voltmeter reading will be 0, then regeneration takes place. Once regeneration takes place, power taken from the supply will reduces because they are exchanging their power. Motor generator exchanging powers. Now, why it is taking a small current from supply now? Whatever the current it is taking, multiply with voltage. Therefore, once switch is closed, then the armatures of generator and motor will exchange their powers. Good stuff. During this, the power taken from supply will reduce. The power taken from supply reduces. Now, how much power it is taken from supply? How much power? VI. V into I. Why it is taking a small power VI? Tell me. That power, whatever now it is taking, V into I. Supply voltage V into I. That is a power. What is that power? VI. V into I. Previously, VIAM is the power drawn by motor armature. But once the switch is closed, and most of the current will supply by generator itself. And now current is very, very less. What is that current? A small current. That V into I will give a power. That power is nothing but losses in both armatures. Why losses? Generator output is input to motor. Motor output is input to generator. Output, input, we are talking. Where is the losses? Who is contributing losses? That losses is contributed by V into I. The losses in both armatures. What are the losses in armature? Armature copper loss plus mechanical loss. That losses is contributed by this VI. Losses is maintaining or supplying by source. They are exchanging their output, input. So that's why V into I is the losses in both armatures. What are the losses in both armatures? VI equals to losses in both armatures. IA square IAM square RAM plus IAG square RAG plus rotational loss. Two motors or two machines, motor generator. That's why 2W0 I will take. Rotational loss of both, 2W0. Now from this equation, you can find rotational loss of each motor. Okay, you will get rotational loss. So here we are not discussing numericals. For numerical point of view, this is required. Otherwise, for theoretical point of view, you should understand when we need to close the switch. After closing the switch, there is regeneration of power. Generator producing electric output that is given to motor. Motor is giving mechanical input to generator. Both exchanging their powers. Okay. Now, approximately we can find efficiency here. Approximately how it is observed. First, with respect to armatures only, we are talking armatures only. Motor armature, generator armature. First, efficiency of motor. Output power by input power. What is the motor input? Output power of motor equal to efficiency of motor into input. Input is VIAM. Okay. What is the input of motor armature? Observe. What is voltage across this armature? V, 240. That is V. Into IAM will give motor input, armature input. Okay. That is only I written here. That is only I'm writing. Output of motor is this. Similarly, efficiency of generator, output power by input power. Here I will take input. Input equal to output of generator is what? Generator armature output. What is the voltage here? V only, 240 no? That is V. Parallel, all are parallel now. Voltage is same for all, V only. V. Okay. Now V into IAG is generator output. V into IAG is generator output. So input equal to V into IAG, generator output, divided by efficiency of generator. Now tell me, this one and this one same or not? Motor output, generator input, same or not? Answer. So why on the last day so much lazy? So up to now you supported so much. Very quickly answer, very interested. But at the last becomes dull. Yes, they are same, equal only, no? Motor output, observe the figure. This is motor output. This is generator input. Both are same, mechanical. That's why now I can equate these two. Now equate both. Therefore, equating both. Efficiency of motor into V into IAM equals to V into IAG divided by efficiency of generator. V gets cancelled. Cross multiply efficiency of motor, efficiency of generator equals to IAG by IAM. As we taken two identical machines, both should have same efficiency. So efficiency square equals to IAG by IAM. If you want efficiency of each machine approximately, you can take square root IAG by IAM. Square root IAG by IAM. This is important because in previous some of the examinations we get options. The efficiency of each machine in Hopkinson test is dash. IAG, generator armature current by motor armature current. IAM by IAG. This type of options are there. Square root IAM by IAG. Square root IAG by IAM. Answer is square root IAG by IAM. Okay, so you should know that point first. The efficiency of each machine approximately this. Okay. If it is conventional question, you should not use this. There is another procedure for that. So there you will see. So mechanical losses is contributed by supply. That's why we are not taking here. Supply will take that mechanical losses. Okay. So approximately using this equation, you can find efficiency of each machine. Okay. Next. This is about Hopkinson test. Next, fourth one, field test. Completed all of you this? Motor output it is, generator input it is. Both equal, both are same. That's why we equated both. And we got efficiency from this. Root IAG by IAM. Next, field test is for series motor only. Yes. Right. Fourth one, field test. Field test. Now tell me why we call it is field test. This test is used for series motor, but in previous examinations they given which of the following test is suitable for traction motor. Traction motor or series motor, both are same. is also called traction motor. Why we call field test it is? Tell me if you have any idea. Why we call field test? Yes, that is not possible. Generator produce 240 is not possible because both identical machines. How it will generate 240? Why we call field test? Fields in series, invented by field to calculate field losses. Okay, simple. However, Swinburne's test, Swinburne's invented. Hopkinson test, Hopkinson invented. Field test, field invented. Yes, whatever is there here, field. That is the name of the scientist, M.B. Field. This is the name of the scientist only, M.B. Field. That fellow name is M.B. Field. That's why we call field test it is. And he used the test for series motor. And in this test, he also taken two identical series machines. He also taken two identical series machines. In that, one is operating as generator, other is operating as motor. And these two are mechanically coupled, but electrically not coupled. Okay. And the main purpose of this test also to find rotational loss, because series machine rotational loss you cannot find under no load. We have to apply a load, we have to find rotational loss from that, and also we can find efficiency. Okay, let's see the procedure figure for this. Two series machines, one is operating as generator, other is operating as motor. Take the figure. Both are mechanically coupled but electrically not coupled. Generator output we given to a load here, not back to motor again. This is not regenerative test. See, this is a motor, this is a generator. Both are mechanically coupled. Generator and motor both are mechanically coupled. Okay. Complete the figure. Okay. See now, here if you observe, the generator is not operating as series generator. It is operating like separately excited generator. Observe. Taken two identical series machine. One is operating as motor, series motor. Other is operating as generator. But the generator field is taken in series with motor here. See, generator field winding is operating like separately excited generator. Okay, like that he taken the field winding in series with motor here. Okay, anyhow, apply rated voltage to motor. See, motor rated voltage is this because V is what? V is the voltage across motor plus across this field winding there is some voltage, that is V. V equals to Vm plus IAM into RSCG. There is some voltage drop now, that is total supply voltage. But by placing one voltmeter across the motor only, apply rated voltage to motor first. Apply rated voltage to motor. Now motor starts rotating, and same speed generator also rotates. So generator is rotating. Then as field current is flowing in this, flux will produce EMF induced, and there is some terminal voltage of generator that is also connected to a load, and current in generator armature is IAG. Now in this combination, we give some input voltage, some input power. What is the input power we given? V into IAM. The input applied to the whole system is VIAM. Okay, we are giving this much input, and you are collecting some output here. This is output. How much output you are collecting? Voltage and current, VG into IAG. This much output we are getting from the system. From this complete combination, this is the output we are getting. Input applied this much, output we are getting this much. Therefore, you will get some losses or not? Yes. What are the losses? Total input minus total output. Then you will get some losses. Let W. This is losses. Okay. This is losses. Some losses you will get. Now, what are the losses in both machines? That we have to write. Okay. Now, next line. Therefore, the total losses W equals to losses. What are the losses? I square R loss in both machines, rotational loss in both machines. That is IAM square RAM. Same current is flowing. Same IAM is flowing in field winding, armature, and this field winding. That's why I will write at a time. IAM square into RAM plus RSCM plus RSCG plus in generator IAG square RAG plus rotational loss of both 2W naught rotational loss. Let us take rotational loss 2W naught. Now you know this value W, input power minus output power. The only unknown in this equation is rotational loss. Calculate that rotational loss from this equation. Currents you know, resistance you can calculate, measure, and only rotational loss you can find from this equation. Okay, so you got rotational loss of the series motor and generator. Now calculate efficiency. What is efficiency of motor? Therefore, efficiency of motor. What is motor equation? Output power by input power. What is electrical in this? Input is electrical. That's why input minus losses divided by input. What is input of motor? Motor input. Observe the figure. Motor voltage is Vm. Motor current is IAM. So motor input means Vm IAM minus losses in motor. What are the losses in motor? IAM square into RAM plus RSCM. This is motor losses plus rotational loss of this divided by input Vm IAM. This equation we use for calculation of motor efficiency. Input of motor minus losses in motor divided by input of motor. Only unknown is rotational loss. That is only mainly we calculate in this test. Next, efficiency of generator. Output by output plus losses. What is the output of generator? VGIAG divided by output is VGIAG plus losses in generator. What are the losses? losses, IAG square RAG, generator resistance, plus in the field winding of generator, which current is flowing? IAM is flowing up. Take care, it is. In the field of generator, IAM is flowing. So IAM square into RSCG. That is only we should take care here. Plus rotational loss of this. So both having same rotational loss because mechanically coupled. Same speed, same loss. So this equation is for generator efficiency. Okay. So two identical machines taken, but we are not operating with same currents now. Both current in generator different, current in motor different. That's why different efficiencies. So use this equation for generator. So this is the calculation of efficiency using field test. The main purpose is to find rotational loss. Yes, generator is like a separately excited generator here. Okay. Yes. If you solve numericals, you will get more idea on this. Up to that, these are calculations directly we are taking from figures. If there is a numerical point of view, you will get some more understanding of this. So there is time, if you want, refer the textbooks. Otherwise, now up to your objective type of examination, you no need to go through this. Okay, just have some idea of test. That's it. No one will ask you in prelims or any objective type of examinations. Next, last one, retardation test. Completed all of you? So here IAM it is, not IAG, because check in the figure. Last one, retardation test. Or running down test. In the name itself, running down. See, very interesting test it is. Simple, small test, interesting. See, this is a no load test. This test is a no load. Under no load only we operate. So as it is no load test, it is not suitable for series. Okay. Now you can use for any other motor. I am taking a shunt motor. Observe this. The shunt motor is taken. See this. Take a shunt motor. Now close the switch, which means that rated voltage is applied to motor. Now adjust the speed of the motor to rated speed. How to adjust? By changing these rheostats, armature and field rheostats. If you adjust, you will get the required rated speed, whatever is there on the nameplate. Okay. Apply rated voltage to the motor by closing switch and adjust the speed to rated speed. Okay. Now open the switch. Test is over. Test is over. Apply rated voltage. Adjust the speed to rated speed by changing rheostats, by adjusting. Then once it is rated speed, if you confirm using a tachometer, then open the switch. Test is over. Test is not over. Test starts now only. When it starts, let us assume at t equal to 0, switch is open. Switch opened at t equal to 0. Once switch opened, from there you have to measure the time. You have to measure the time, in how much duration of time the speed reduces to 0. Because whenever switch open, supply disconnected. Then is the motor immediately stops? No. So that is we know. Practically every motor will run for some time. Slowly it becomes 0 speed. Now in what duration the speed of the motor becomes 0? That duration you have to count using uh, timer. Let us count in what time the speed becomes 0. In how many seconds it becomes 0. Calculate that. That is nothing but why the motor is rotating for some time, due to some energy stored. What energy stored? Kinetic energy stored or motional energy stored. Because of that it is rotating for some time. So here the stray loss of machine or motor is nothing but the rate of change of kinetic energy, the rate at which kinetic energy becomes 0. Rate means in what time kinetic energy dissipated. That is nothing but definition of stray loss. So stray loss we can find by calculating the rate of change of kinetic energy. Because of kinetic energy only it is rotating. Now tell me example, in your home, assume that there are two ceiling fans. So definitely two will be there everywhere. Assume that two ceiling fans are there. Let us switch on both and allow the two fans to rotate at its highest speed. Using regulator also allow at highest speed. Okay. Now switch on the two fans at a time. At same time switch off. Switch off the two fans at same time. Now observe the two fans. Is the two fans will stop at same time? Is the two fans will comes to 0 speed at same time? No. Definitely they don't come at same time 0 speed. Maybe one fan will reach 0 first and other fan will reach after some time 0. Means come to stop. Now tell me, out of the two fans, which fan is having more stray loss? The fan which stops first or which stops second? Which one will have more stray loss? First stopping, second stopping. Which one is having more stray loss? First stopping or second stopping? Okay, some of you first, some of you second. Okay, the answer is the fan which stops first is having more loss. Why? Because observe here, stray loss is inversely proportional to time duration in what it becomes 0. If a fan quickly stops, means the fan comes to 0 speed quickly, means time taken is less. If time taken is less, it is having more stray loss. So simple, if a fan quickly stop means more loss in that. If a fan running for long time and becomes 0 speed means that is having less stray loss. That is the efficient fan, because for long time it is rotating means there is a good bearing setting in that. Good bearing is good. That's why smoothly for long time it is rotating. That is having less amount of loss. And which stops first will have more stray loss, because less time is more stray loss. Okay. Now how to find that kinetic energy? Simple. What is the formula of kinetic energy of rotating masses? Don't say half mv square. Half mv square for moving linear velocity. It is rotation. In a rotational system, half j omega square. It is the kinetic energy. Now substitute that kinetic energy here. The stray loss is given by rate of change d by dt of half j omega square. This is equal to 1 by 2 constant. Moment of inertia j also constant. Differentiate with respect to t, it is we get 2 omega into d omega by dt. 2 cancel. Therefore, the stray loss is what is that? 2 cancel, j omega into d omega by dt. J omega into d omega by dt. Okay. So if you know the value of j and if you know the value of omega and omega also, then we can find the stray loss. So they will give that omega values and all in the equations, j omega all values. Then we can find by differentiating that omega equation with respect to t, we get some value here. That is nothing but stray loss in watts. Like that, we can find stray loss of motors by conducting this retardation test. Why we call running down test? It is running down because once switch is open, what is happening? The motor is running down. It is that is called running down condition. The motor is running down to zero speed. The motor running down to zero speed. That is called running down test. Okay, simple. The rate at which the speed is initially rated at that time. Once the switch is open, the speed reduces to 0, 0, 0, 0, 0. Now, in what duration? Calculate what is the time taken to become zero speed. That will give the stray loss of the motors. Okay, in what speed, in what duration the speed of the motor becomes zero, that we need to calculate in this test. Okay, so this is about retardation test. See, brushless DC motors and these are all. So actually we don't have in any syllabus. In ESC also you don't get anywhere. So already we discussed so much. There is no time also. So you refer in textbooks like Generalized Theory of Electrical Machines by Bimra once. If you want any additional topic, go to Generalized Theory of Electrical Machines by Bimra, by P.S. Bimra. Okay, this is one book and some special motors also there in J.P. Gupta. Go to J.P. Gupta also. Okay, so whatever we have already, it is so much. This is the most important. Whatever is less important, just neglect that. Okay, no need to go through that. Okay, first be perfect whatever is there with us, and whatever is not there now newly, no need to learn again, because no guarantee from where we get the questions. The only thing we have to do is revision. At least 2 to 3 times minimum you have to revise. So 2 to 3 times means so much time it will take. But first time it may take nearly we taken 40 hours, for example. For revision, you will take first time 30 hours. For first time, if you revise, minimum 30 hours will take. And for second time, it will take only 20 hours. And third time, when you revise, try to complete it is in 10 hours only. Revision quickly. Revision means at that time we no need to solve every question. No, just having a direct eye contact with each and every topic and question models. That is enough. At the last, it is revision. Okay, so anyhow, no need to tell all this. You are very well thinkers. Like you can understand what is going on the situations right now everywhere. So everyone is aware of everything. Okay, you are not a small kid student. So you know everything. So be perfect. Prepare like anything in this 3 to 4 months time. Prepare like anything, because without struggle nothing is possible. Without hard work nothing is possible. Don't depend on the luck. Luck is very very rare. Okay, don't depend on that. Struggle like anything in this 3 to 4 months time. Enough. Yes, DC series motor singly excited only. for EC mains during prelims preparation, self. So during prelims, see, whenever you are going to prepare prelims, no, don't look at mains model because it will take so much time. It will consume your time. For prelims, whatever objective type you are preparing for GATE, that is enough technically. But go to and concentrate only general studies. Okay. So I think I completed transformers. Transformers we complete for previous batch, and I don't know how many new batches are there in this again. Okay, we will see later. ISRO exam is completely conceptual. It is easy only, but there is negative marking that you need to take care of. That ISRO. ISRO is easy only, not tough one. But there you should have good knowledge in analog signals and digital. From there also we get more number of questions. See, no need to go to textbooks right now. Don't go to any textbook. It will consume your time. Whatever is there in your notes, prepare that. And only for problems, see, because if I solve n number of questions also, if I solve n number of questions, the n plus 1 question is again new to you. If you see n plus 1 question, again it looks like new question. Like that, there are n number of questions. Okay, whatever is possible, different models I covered. Still, if you want, go to the standard books example questions. Example like JP Gupta, PS Vimra, Nagarath and Kothari. So these are enough. Go to that books and try to refer some example questions if you have time. Prepare little general studies because that is also important for prelims. Okay. So all the best to everyone. So very patiently sitting and listening and responding is very difficult from your side also, I can understand. Never ever say that machines is difficult. The easiest subject is machines. Okay, thank you everyone. So that is not yet decided for revision when it is or not. So most of you responded well in this batch. Good. Yes, transformers I only will take. And those who have new one, so take the number. This is Telegram only will work with this. Telegram username, I think, I don't know. I think my name only will be there or KB will be there. Anything. So I forgot what is there in the username. Okay. Okay. So now your turn it is. Try to revise properly as much as possible. Earlier revision is best because If you revise now itself, just after completion, so whenever the new subject is going on, in between at least 2 to 3 years daily, try to revise the previous topics, because no more gap should not come. If there is 10-15 days, okay, but if 20 days or more than that, if gap is coming, every subject will become new only. It will take so much time. Yes, same. KB_S1. So I don't know about induction when it starts.
Hello, sir.
Tell. Yes.
Good evening, sir.
Mm.
Sir, we have only 6 tests in the DC machines now, sir.
What?
Now we are discussing about the tests.
Ah,
Sir, is there any test for the generator?
as for
Generator. We are discussing only the motor now, sir.
generator like that separately we don't have. Here we have some combined series generator motor we are using. But for generator separately, we don't conduct this retardation. Retardation test is only for motor valid, because generator we are rotating with mechanical input. Na, again.
Yes, sir. But we want to see what is the performance of the generator also.
Generator means load test directly, because connect some resistive loads and measure output power, input power. That is output
First
by
test.
output plus losses. Load test only, direct test.
Okay, sir. Sir, one more, sir.
Hmm.
Sir, as we using a starter for the reducing the starting current only, sir.
Starter?
Starter using only for the reducing the starting current.
Oh, yes.
Sir, if you use the starter with the series motor, we are
Oh.
not giving any load, then also we can reduce starting
No,
current
no,
also.
no, 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 no. So series motor particularly, we have two types: no load protection and load protection. Both should be there, because for series motor, no load we cannot operate. No, if you start in no load, it will rotate at dangerous high speed. It will damage. That's why we
Yes, sir.
have no load protection also in that.
But
Hmm.
but in starters we have starts no only no, sir. That we reduce the starting current also.
Starters.
We have the resistance as a starts.
Oh,
It's reducing the starting current.
but how much reduce? How much resistance we are adding? Very small resistance only. No?
Okay,
So already in series motor, starting current is less only. That is not high current, because at the time of starting, current is high. You are asking if you put resistor, what happens? No.
no, sir. Means as we using the starter for the reducing the starting current, no, sir.
Hmm.
If you use a starter in the DC
Hmm.
machine series motors,
Hmm.
at the time we can reducing the starting current without using the load. I'm asking that. Hello, sir.
But that reduction is less only now, because IA of series motor is V by V minus EB 0 by RA plus RS. You are saying that adding so much resistance in that, then automatically current is limited.
Yes, sir.
But how much resistance you are adding? Voltage is 220 divided by RA some 0.1. How much resistance you are adding? Maybe some 10 ohms or 12 ohms overall you are adding. This is also still high current only, no?
Yes, sir.
Okay, current is limited. That is only we are doing the same thing, no? In shunt motor also same thing we are doing. Adding a resistor that will limit some current, but immediately back EMF will generate, no? After that,
Yes, sir.
when back EMF is coming, automatically current again reduces. Still reduces. Same operation like shunt motor, only in series motor.
Okay, sir.
So you see
Sir,
one time in PS Beamdot 2 point starter, you will understand clearly.
okay, sir. Sir, one more, sir. These many tests are only for in the laboratory we use, or is
Hmm.
any technical we are using?
No,
Sir?
no, only lab purpose we use. Lab test only there.
Sir, is there any test in the industrial for the DC motors?
Industrial means we use that is direct load test. We use direct load test, because we need to decide what is the current rating of the motors and motors, na, particularly. For
Yes,
that we
sir.
use load test directly. Just like brake test only, we use their load test, and we will measure how much current it is drawing and heating. Same explanation like Sumner's test of transformer. Same as it is, we do load test. And resistance measurement test we have to do, because resistance calculation of armature resistance and field resistance in the field winding and armature winding. So these are some factory level test. Not only this, if you see induction machine and synchronous machine, additionally we do there in the factory level, like noise level test, there also we do, because induction is having interference level test also. Just like transformer, whatever we have, additional test we do in induction. Synchronous also same, noise level test is important. And in synchronous machine, another one is insulation level test. Whatever we are using the insulation for windings, that is also we do. Same as it is transformer, we discuss. In that, some test valid for rotating machines also.
Okay. Sir, I have confusion in that. In motors, we are using E equal to or equal to EB into IL at some time, and sometimes we are telling that E equal to VL into IL, sir.
E equal to
EB into IL.
that is mechanical power equation, no? And input equal to electrical, that is VIU.
Means it's in some problem we are using the mechanical force. So
Direct power constant means you can take anyone, because if input power is constant, output also constant only, no?
yes, sir.
That's why anyone we can use. Based on the question, what is they are asking, what we need to find, based on that we will take it is.
Okay.
Okay.
Thank you so much, sir.
Will we have course for IIT and PSU interviews? So separately you don't have any course, but after GATE, sometimes we conduct mock interviews. Particularly for engineering services, we are conducting mock interviews, but not for PSU separately. Okay, so you follow website, you will get the updates. Okay.
Hello, sir. Sir, sir, sorry. So DC machine 50 Hz we are using supply. Sir, if your brushes are rotated with means with the shaft, it will supply with how many volts, sir?
The brushes?
If the brushes are shifted with on the rotor, means shaft, sir, rotating. It will rotate. It will give only AC, no, sir. Output power is AC.
Your question is not. Your voice is breaking. So you send that is in Telegram. I will check. Why do brushes have spring in motor? That is, I already said, no, brush holder and brush. This is a brush. So why we use spring in the brush? Because the brush should be tightly attached with the commutator surface. When it is possible, if there is a spring, this is a brush. Whenever it is rotating, because of friction, size of the brush will get wear and tear. So whenever size of brush is reduced, who will push the brush towards commutator surface? Suppose if there is no spring, who will push? If there is a spring, because of brush, while placing the brush, we will tightly press the spring. Then we place the brush there. Whenever size of brush is reduced, automatically brush will come closer to the commutator surface. It is attached continuously. That's why. Okay.
Sir, I send it, sir.
Field winding of a 4-pole separately excited DC machine excited from 50 Hz supply. Armature is rotated at 1500 RPM and the brush rocker is also rotated in the same direction at the same speed. Voltage across the brushes. think it is 0. How
Sir,
much
answer
given?
is D, sir.
Oh, it is how both rotating in same direction. No? Armature rotating at 1500 rpm and brush rocker means, see, this type of questions you no need to go because you should have a proper reason na, here. What is brush rocker given? Brush holder
Sir,
we
brush
have.
rocker means fish holder, sir. I think.
It is also rotate. Actually, brush holder never rotates. How it is possible?
I think that brush is on the shaft, sir, is telling us that
Mhm.
as the shaft is rotating, brush also rotating. It's telling.
Okay, I will check and answer to you that. Why do see for wave winding, like lap winding, same example you take and try to construct wave winding, you will understand. So wave winding will not get complete. So for wave winding, we need to take, suppose there are four slots, then 4 poles. There are 4 poles. Per pole, let us take 3 slots. Now total how many slots? 12 generally. This is for lap winding suitable. Now let us take same wave winding for 12 slots. Your wave winding will not get complete. You will understand if you see if you draw the figure. Okay. For wave winding, when it is 4 pole, you need to take 12 slots. You should not take. You should take other than that 13, 14 slots like that. Then only it is possible. Okay. So these figures are not required. Just remember that point enough. Okay. Good night, all of you. Take care.
Sir.
Hmm.
Sir, could you open that one Telegram, sir? I sent that question.
Which one?
Could you open that Telegram?
Hmm.
Sir, in this, the current is 1.
Dynamic braking means what is the equation? EV
V
by
by R plus
RA
RB.
plus RB.
It's
We
telling
need to
1.2
limit
times, sir.
1.2 times, multiply with 1.2.
But in answer, it's not multiplying 1.2, sir. That's why
That is wrong. You should multiply with 1.2. Then only you will get some value of RB. That is only correct.
okay. So means that answer will be wrong.
Yes.
Okay. Good night, sir.
Good night.